For our MAE 152 project, we decided to perform a variety of studies on components of a scale model we call Duster Plane. Currently, the Labor Research Group on campus is using a following CAD model to 3D print a plane and conduct experiments inside a wind tunnel. The first part we did a study on was a steel strut landing gear. The design was based on the image shown to the left and expected to find the high stress points on the model during the landing. The first analysis we performed was a static analysis on the landing gear, which was made out of alloy steel. We fixed the landing gear in two different methods, the first being fixing only the top bolt hole and the second fixing both the bolt hole and the entire top face, which would be pressed against the underside of the airplane. We applied a load of 100 newtons in the positive C direction in order to simulate a hard landing. This value was based off the estimated weight of the model, which was roughly around 1 kilogram. Based on this first case, it had a maximum viscous stress of 384 megapascals and a second max stress of 104 megapascals, with a yield stress of 604 make the part not yield. The final analysis performed on the landing gear was a fatigue simulation. This simulation was important because the landing gear would have to perform tens of thousands of landings over the course of its lifetime, and it is important to know when it may fail so that it may be replaced before a catastrophic failure. The simulation was performed using the values from the static analysis and resulted in the life expectancy in the first case being 14,410 landings and in the second case being 24,310 landings. The difference between these two numbers is likely due to the more concentrated forces in the first case causing an earlier failure. For the iteration analysis, the landing gear was modified in two different stages in the hopes of decreasing the maximum bomb missile stress experienced by the landing gear. In the second iteration, the part that was modified so that the high stress areas along the curves were increased by fillet radius, which allowed a more distributed force load of a 4.9 decrease of max stress experienced by the landing gear. In the final iteration, the part that was modified to increase the thickness of the curved piece, which led to a 9.1 decrease in the max stress experience when compared to the original model. The key forces acting on an airplane during the flight are both lift and drag. The faces wing normally attached to the fuselage were fixed during all studies and standard mesh was applied. In the lift study, the forces were directly vertically in the C direction across the wing using the top plane as reference. First, we perform a lift and drag force analysis with different force loads and directions applied. In the first case, we got a max stress of 27 megapascals. In the second case, we got 31.56 megapascals. The forces in the drag study were also applied to the faces of the wing. Finally, small model analysis was done to simulate the small vibrations of the wings, which was caused by turbulent flow using aluminum alloy material. Two iterations both in the lift force comparison and drag force. For the lift force comparison, we realized that the titanium alloy had a far greater yield strength than the aluminum, but one must consider the strength to weight ratio when designing a plane wing. That's when taking account the drag force in the wing, the trapezoidal wing had a greater increased max stress from the geometry change accredited to the larger surface area. There are 5 key forces that an airplane propeller can experience. The propeller can experience centrifugal, torque bending, thrust bending, aerodynamic twisting, and centrifugal twisting forces. For the propeller, we developed 2 main static analyses in which we compared different scenarios for the propeller that it can experience. For the thrust bending analysis, we performed a static study in the positive C direction of 5 newtons. To further analyze the propeller, we applied a boundary condition of a fixed geometry to the blade touching the base and let the other part of the blade be a roller. For the load, we varied the direction of the forces and also whether the part had a centrifugal or a thrust bending force. The overall part did not experience yielding and the displacement was kept below 0.00139 inches. For the static analysis iterations for the propeller, we applied 2 different designs, one in which the blade was rotated 45 degrees and another one with the blade rotated 45 degrees and reduced weight about 25%. As a result of the iterations, the percent error was increased but the blade displacement was reduced. Thank you.